So for experiment 12, what you're going to do is you're going to just make a copy of this, the flow chart. Oh, for experiment 10, everything, all of them. And so you'll include all the trials, all 8 of them. For this experiment, the qualitative analysis, you're going to make a copy of this flow chart and then write the reactions like I did in class. I already wrote all the reactions down, I think. This one I might not have broken up into 2 parts. You know, the first part is just double replacement. Manganese 2 hydroxide with nitric acid yields manganese 2 nitrate and water. And the second part is the manganese 2 ion being oxidized by sodium bismutate to permanganate. How was that? Yeah, that's the 4 trials I know only appear. You have to add more. And so if we look at the titration, go back. Experiment was that. There's only room for 4, so you'll have to attach a sheet of paper and then put more trials on there. That's normally what happens. You know, I might have hit the record on the number of trials. You know, but this often happens. If you don't get it within 4, you have to do 5, 6, 7, 8. They only included 4 because most people hit it within 4 trials. For some reason, well, I know the reasons, but didn't quite hit it in 4 trials. Okay. All right, so this one, we did all the calculations for this. The only one, the additional calculation is, since we didn't do part 2, in part 2, you're analyzing an unknown acid, and you're going to determine the concentration of this vinegar solution, and then compare it to the actual. So what we did was we calculated the concentration of the sodium hydroxide solution here. And we got the average, but I know what the concentration is supposed to be. And so I gave that to you. It was supposed to be 1024 according to Stockroom. And then we calculated the percent difference. So we did an additional calculation here. Okay. Again, for the qualitative analysis, what I want to see for that is I want to see like the flow chart and the reactions, the equations for the reactions associated with the steps here, with each step. You know, I just did, I didn't do all of them though. You just do the ones that you see a reaction, you know. Some of them that we didn't, like for example, barium, you know, barium ion plus HCl yields no reaction. So I didn't put all these no reactions here. Manganese ion, 2 ion plus HCl yields no reaction, etc. So you don't have to include all the no reactions. Just put in all the reactions that we had here. And I wrote those already on the flow chart. And so you do the same. And then what we're going to do here is we're not going to fill this out, you know. And so all you're going to do is you're just going to attach a sheet of paper and tell me, you know, we actually tested 3 solutions. And so you just write the observations of the 3 solutions. We had 3 unknown solutions. And so solution A, you don't have to write out all the observations, but just tell me what we tested positive for. You know, solution B, tell me what happened with solution B and what we tested positive for up to a point. you know, we didn't make it very far because that's the one that the test tube got a hole in it and leaked out all the solution. So we weren't able to go beyond and test for beyond lead and test for barium and manganese. But solution C, we did that one to completion. So tell me what we tested positive for here. Solution A and B, I think we did the anions, but solution C, we did not do the anions. This one. Yeah, so what cations, anions, cations, anion. And then a little note, you know, what happened. And the solution C was just cation analysis. Should have done the anion, it wouldn't take them that long. Okay. So is that clear for the qualitative analysis? All right. So I need to continue with, let's see, lecture. I have some PowerPoint. Let's see, PowerPoint 16. Did I put up PowerPoint 17? Yeah. All right, chapter 17 deals with acids and bases. We already talked about acids, bases. So we're going to add a couple of things here to what we've discussed. When we're talking about acids and bases, we can look at it from three different perspectives: Arrhenius, Bronsted, Lowry, and Lewis. Lewis is like the universe of acids and bases. And sometimes studying the whole universe of acids and bases is too much. And so Lewis is the entire universe of acids and bases. And then Bronsted-Lowry is like a smaller subset of this. So Bronsted-Lowry. And sometimes it's just easier just to study a certain subset, like, you know, rather than study the entire universe, you study one galaxy or one solar system or something like that, rather than, you know, a huge number. I don't know how many galaxies there are, but some huge number. And so sometimes it's just easier, you know, to narrow down the field, but that means we're missing all these. So Bronsted-Lowry misses all these acids and bases that aren't part of this little subset here. And so things like CO2. CO2 is not a Bronsted-Lewis, or not Bronsted-Lewis, Bronsted-Lowry. Bronsted-Lowry. CO2 is not a Bronsted-Lowry acid, but it is a Lewis acid. So CO2 falls out here, but carbonic acid is a Bronsted. And so carbonic acid falls here. It's this carbonic acid decomposes into CO2. CO2 is still acidic. And then we have an even smaller set, you know, so if you're looking at the Bronsted-Lowry universe, then a small portion of that would be the Arrhenius. Arrhenius acid is just anything that gives H plus to solution. So essentially Arrhenius acids are just H plus AQ or H3O plus. We use these interchangeably, H plus and H3O plus, and OH minus. So it's very narrow, you know. Arrhenius acids and bases are just H plus or H3O plus and OH minus. And so it's a very small subset here. So Bronsted-Lowry doesn't have to be aqueous. Bronsted-Lowry acids can be gaseous, like HCl gas and ammonia gas. You know, Whereas Arrhenius isn't. Arrhenius is all aqueous like this. And so Bronsted-Lowry catches more of the acids and bases that Arrhenius doesn't. Arrhenius is very limited. And then Lewis captures all of them. And so this is Arrhenius here. This is Bronsted, that's Lowry. This is Lewis over here. We spent all our time looking at this part of the acid-base universe. You know, we did a little bit of Lewis, but not really much. We spent all our time looking at just Bronsted acids and bases here. The reason is if you look at the Bronsted acids and bases, it follows a simple pattern in terms of reactions. Lewis is a bit more complicated, you know, as far as reactions go, reactivity goes. You get more into it in Chem 1A than Chem 4, so I'm pretty much going to skip a lot of the Lewis acid base stuff. Well, there are acids here, you know, things like vitamin C or citric acid, fruits, you know, carbonic acid, phosphoric acid, boric acid, sometimes in beverages, and bases too. This is sodium hydroxide, red double lye. This is a drain cleaner. That's solid sodium hydroxide. I had that. Soaps, detergents. You know, a lot of detergents contain phosphate. Phosphate's actually a pretty good base. You know, it's not a strong base, but it's borderline strong base. Borate. You know, bases tend to be slippery and feel like soapy. Acids and bitter. Actually, bases, if you ever tasted soap, it tastes bitter. Don't taste red double lye, though. That'd be bad. Acids are sour. So here, let's see. This is sulfuric acid here, except we usually write a more detailed. I don't, you know, this is a poor habit to get into so early. You know, you got to write in the lone pairs here. Otherwise, you're going to have a problem in the future. Unless you can see the lone pairs without even looking, you know, then you'll have a problem. Then we could do the formal charges. This is sulfuric acid without the, you know, expanded octet. The formal charge is a little bit high, +2 on sulfur and -1 on these two oxygens. Compared to if we put double bonds. If we put a double bond here and a double bond here, then all the formal charges go to 0. And so most people write sulfuric acid, you'll see, as 2 double bonded oxygens like this. We can put the hydrogen anywhere, you know, because this is not a 3-dimensional. This should be tetrahedral. And so I'm not drawing it. Loose structures, you don't have to draw 3-dimensionally. When we do the wedge and dash diagram or the 3D drawing, then we want to be a little bit more accurate in terms of the shapes. But anyway, sea slug excretes sulfuric acid. Here, the tartness of lemons and oranges comes from the weak acid, citric acid. The acid is found widely in nature and in many consumer products. There's a huge amount of citric acid in lemons. Caffeine is what we call an amine. It has this nitrogen, these nitrogen groups, so ammonia-like, you know. And so those are basic. And so it's weak base, caffeine. Those are the means. You can see the blues are the nitrogens here. Depends on how the nitrogen is bonded as well. You know, that's going to dictate certain things. Cabbage, you know, cabbage juice is used as an indicator. Cabbage juice has colors that depend on what we call pH. You know, pH is how acidic or how basic the solution is. And so the more acidic it is, we have this red color. The more basic it is, we have this yellow color here. And we have some intermediate colors between the two here. And so it's what we call an indicator. It indicates the pH by the color. Coral, this was dead coral, but coral is mostly calcium carbonate, and calcium carbonate reacts with acids to form CO2 gas. It makes carbonic acid, which decomposes. So one of the properties of acids is It'll react with bases, react with carbonates. Carbonate's a base here. It also is an oxidizer, and so it can oxidize zinc metal. So you can dissolve zinc metal in acid like this. It could be vinegar, it could be hydrochloric acid, etc. Properties. So when we're doing Bronsted, you know, we could do Lewis. Actually, no, we aren't going to do. We'll do Lewis later, but Arrhenius is pretty easy. Arrhenius is just H plus and OH minus, or H3O plus and OH minus. So Arrhenius is only one reaction. You know, it's H plus and OH minus mixed water. In Bronsted, it gets a little bit more complex, and so we spend a lot of time looking at Bronsted. So, for example, this is acetic acid here. Acetic acid and water. In this case, acetic acid is the acid, and water will be the base. Water can go either way. And so water is going to pluck a proton off acetic acid, form hydronium and acetate. And so this is a Bronsted acid-base reaction. The situation here, though, is there's no driving force. If you look at this particular reaction, you know, we've been looking at driving forces. So we look at acetic acid. This is our acid going forward. This is our base. Now, if we were to go backwards, hydronium would be our acid and acetate would be our base. If we went backwards here, hydronium loses, acetate gains. Now, when we compare the two acids, hydronium is a stronger acid and acetic acid is a weaker acid. And acetate is a stronger base, water is a weaker base. So we would say there's no reaction here. No reaction. But let me put that in quotation marks, because even though reactions not predicted for this, a tiny bit of reaction occurs. A tiny bit of reaction occurs because of collisions, you know, and then not all molecules have the same energy. There's a small fraction of molecules that have quite a bit higher energy. And if those two actually react, we could get some reaction. And so what turns out to happen in this case is a little bit of reaction occurs, but mostly it's mostly this. And so this is favored. This is not favored. And we expect the driving force to be this way. We're going to go from stronger to weaker, you know, weaker acid, weaker base. And so the driving force is reverse here. But what we can visualize this is like a hill, you know. And so one way to think about this particular reaction is how steep is this hill? And so you have most of the molecules over here. Most of the molecules like to be down here. But some of the molecules can actually climb up. You know, the highest energy ones can climb up here. And so these would be like waves on the beach. You know, sometimes the water can make it up pretty far up the beach. You know, just the highest energy ones make it up pretty high. And the same thing here. This is going uphill. So you'll have a small fraction of molecules that make it up here, but the bulk of the molecules are down here. And so this is why we say the driving force is downhill this way, going backwards. But that doesn't mean a little bit of water can't go uphill here. It's not stable. So this is not stable. It's strong. So it'll react and go back downhill. So it'll react, go back downhill, but you can't stop the waves from coming. And so the next wave's going to come up and you'll get some new molecules here. And so this is what we call a dynamic equilibrium. Dynamic equilibrium here is that, you know, we're always going to have these collisions, and the collisions are going to produce this, but this is unstable. This wants to go back downhill, so we'll go back downhill, but the next wave comes, or the next collision comes, and then forms a little bit. And so what we end up with is something like this: 99.9, this is greater than 99.9% of the atoms are on the left here, and less than 0.1% make it up. So 99.9% of the water is down here, but about less than 0.1% of the water makes it up here. And so the same kind of deal happens here. And so we get partial, this is called partial reaction. Partial reaction. because then we can see the driving force. So it's not so black and white, you know. Our driving force either predicts reaction or predicts no reaction. Well, sometimes, you know, the steep, you know, when we have no reaction, it's too steep of a hill to climb. So the waves could be crashing here, but very little of the water is going to make it over here. This is the reactants, this is the product here, like that. Here's the reactants, here's the products. Okay, this isn't such a steep hill to climb. And so maybe 0.1% of the water makes it up here. And then if this is no reaction here, because, you know, we're going uphill, it's becoming a lot less stable from going from reactant to product, then reaction would be steeply downhill here. You know, if this is reactants up here and this is products, that's a steep downhill. So we get good reaction here. And so in stoichiometry, we deal with these two scenarios. In stoichiometry, it's either no reaction, nothing reacts, or it's 100% reaction, you know, driving force here. And so we assume 100% reaction. And so we got 0% reaction or 100% reaction. But in reality, it depends on how steep this hill is. If this hill is steeply downhill, then I would expect it to be 100%. Everything should fall down here and should be too steep to climb back up all the way. And the same thing here, you know, this is too steep of a hill to climb up. And so none of the water makes it all the way to the product here. But if the hill's not too steep, that is, the difference in energy between the reactant and the product is not so great, then we'll get a situation like this, where we'll form some product, but that product will revert back to reactants. And so we get this circle occurring. And eventually what happens is we reach a state where the forward reaction rate is equal to the reverse reaction rate, and we get a state of dynamic equilibrium. That is, in the dynamic equilibrium, we end up with 99.9% this and about 0.1% this. That's dynamic equilibrium. It depends on how steep the hill is. If this hill isn't so steep, we might end up with 50% this, 50% that, you know, if it's just horizontal. And so if it's just horizontal, then neither side's favored. So, you know, it should be a 50-50 mix. Or something of that sort. Well, how steep of a hill is it going to be? Well, how steep of a hill it's going to be depends on what, you know, our starting acid is, you know, and what our base is. You know, if our starting acid's strong, like HI, and our starting base is strong, like oxide, then this is a pretty steep hill right here. Because what's going to happen is HI reacts with oxide, and it's going to produce the weaker conjugate acid, hydroxide, here. And so when we compare the two acids, HI versus hydroxide, well, HI is much, much stronger. In fact, hydroxide, we don't even consider an acid. We consider that a strong base. And so in other words, this is a huge downhill here. Now, on the base side, it's the same thing. We go from oxide, an extremely powerful base, to an extremely weak base, iodide. And so in this case, this is extremely downhill, although it's inverted, you know, to think of it that way. And so that's a huge hill to climb. So it depends on the difference. Now, if they're much closer in strength, then there isn't going to be much of a driving force, not nearly as big of a driving force. And so let's say we're reacting, HNO2, the acid, with, this is formate. We're reacting with formate, the base. And so HNO2 reacts with formate. And so formate gets converted into formic acid here. And HNO2 gets converted into nitrite here. So in this case, we're going from a stronger acid, nitrous acid, to a weaker acid, formic acid. but there's not a huge, it's not a huge downhill thing there. And here we're going from a stronger base, formate, to a weaker base, nitrite. But it's not a big difference. And so the driving force isn't as big. So in this case, we expect more of a mixture, you know, where in this case, we expect 100% reaction. This case might not have 100% reaction. This case, you know, if they're very almost the same in terms of strength, you know, we're going from stronger acid to a weaker acid, but the stronger and the weaker acid are almost the same in strength, then it doesn't matter, you know, water is going to flow both ways and it doesn't have a preference, you know, neither way is really downhill. And so we're going to expect much more of a 50-50 type mixture, you know, in a scenario like that, where, you know, the water can be on both sides and it's favored that way. And so it depends on the tilt of this. How much? Is it 90%? Is it 80%, 70%, 50%, 10%? Reaction that we get. And so this is the acid and base chart in your book. This is the one from chapter 17. However, the one I have on Piazza, that's from the Chem 1A book. So I just use the one from the Chem 1A book, but they're very similar. You know, what they selected, there's some minor differences, species that they selected, quite similar. Now, going uphill, I guess, no wonder this doesn't erase. Going uphill depends on how high we're going uphill, you know. And so if we're starting, let's say we're starting with HSO3 minus as the acid and HS minus as the base, you know, we're going to react these two. And so HS minus gets converted into H2S. That's what we have. And then HSO3 minus gets converted into SO3 2 minus. And so in this case, we're going from weaker acid to stronger acid. So this is going uphill. It's not favorable, but it depends on how steep of a climb that is. If we're going from here all the way up to here, then this is a steep climb. You know, it's a lot. So that's a huge, huge energy barrier to overcome. However, if we're going from here to here, maybe that's not as steep. And so maybe it's like 80% reaction. I mean, you know, 80% or maybe 20% reaction. It all depends, relative. So let's take a look at some reactions here. This is nitric acid and water. So water will be the base, nitric acid is the acid. This is going to form hydronium and nitrite. Okay, this one should be favorable because when we compare it, okay, this is the acid. This is the acid going forward. This is the base going forward. You know, if we were to reverse this reaction, then hydronium loses the proton and nitrite gains it. Nitrate, excuse me, gains it. So this is the acid, this is the base. And when we look at the chart, which one is the stronger acid? You know, nitric or hydronium? Let's take a look at the chart here. Let me see if I can erase these. No. Okay, so we're looking at nitric acid and hydronium. So this is favorable. There's driving force. It's not huge, you know, because they're kind of close, but still it's downhill. And so we have nitric acid and water. Water is the base. And so nitric acid is going to form nitrate, and water, when it reacts, will form hydronium. And so that's favorable. I'm going from stronger to weaker. Here. In this case, who's gaining the proton? Here, ammonia is a base. Normally it's thought of as a base, and actually it is gaining a proton. Water is the acid. And so up here in the previous one, water was the base. In this one down here, water is the acid. Ammonia is the base. And so water gives up a proton, ammonia gains that to form ammonium, and we're left with hydroxide, ammonium hydroxide. So we compare it going reverse. Now, if we go reverse, ammonium loses a proton. So this is the acid going reverse. This is the base. And then let's take a look at the driving force here. And so back here, it was stronger acid, stronger base to weaker acid, weaker base. Down here, we're going from, okay, let's compare the acids, ammonium versus water, which one's stronger? So for acids, we have water, which is here, and we have ammonium, which is here. So we're going from ammonium to water. So we're going from stronger acid to weaker acid. So stronger acid to weaker acid, and the bases must follow. That is, ammonia must be a, did I do that right? No, I didn't do that right. Did I? Ammonium's stronger, sorry. Ammonium is stronger here than water. HI is the strongest, so ammonium's stronger. This is weaker. Okay, and that means that hydroxide is a stronger base than ammonia. That's the case. Ammonia is a weak base, hydroxide is a strong base. So we're going from weaker to stronger. So normally we'd say this is no reaction, NR. But it depends on how big the difference is. So let's take a look. Okay, so here's ammonium, and here's water. And so it does look like there's some bit of difference there. When we compare the two acids, ammonium is stronger than water. And so it appears that there's no reaction, but in this case, it's not so huge, you know. It's not like a difference between, this is going uphill this much, but it's not like it's going uphill all the way up here. And so maybe this is surmountable. Well, it is a little bit. This is going uphill here, and it turns out there's about 99.9, similar to the last example we looked at, 99.9 and 0.1% of this. And so greater than and less than. And so about 0.1% of the water or the molecules can make it up here. If I'm using the wave analogy, it's the water. All right, here's an example of a Lewis acid base. Lewis acids are electron pair acceptors. Lewis bases are electron pair donors. So look for electron pair that can be donated. If we look at BF3, BF3 is shy of an octet. Again, they didn't draw the lone pairs. So the fluorines have octets, but the boron doesn't. Here, boron only has 2, 4, 6. So we need a Lewis pair donor like ammonia. Here, and we form this. It's called an adduct, AB. And so the electron pair is donated, forming a single bond here. Here's another example of a Lewis acid-base reaction. BF3 is a good Lewis acid because it's shy. In this case, they wrote the lone pairs, fortunately. I don't know, unfortunately, they didn't write it there. And here, they're going to show it. The oxygen is just going to attach to boron here. Now boron has an octet, whereas it didn't before. So that's what makes boron a good Lewis acid in these compounds here. Another example of a Lewis acid-base reaction. This is aluminum chloride reacting with another chloride. This actually has a name. This is called tetrachloroaluminate ion. It's tetrahedral in shape. So, and this just normally in Lewis acid-base reactions, we show what's happening with electrons. And so we can do that here. And these electrons will attack the Lewis acid. And we end up with this. Normally we think of aluminum chloride as ionic, but in this case they showed as molecular here. Okay. Let's take a look at some other ones here. Show. Here's another Lewis acid-base reaction. This is iron here is a Lewis acid. This is in heme or hemoglobin. And then the Lewis base here is O2. So O2 can donate a lone pair. There are two lone pairs here. It can donate a lone pair to iron 2 here. And when it donates it, it forms a covalent bond. So there's a covalent bond between the iron and the oxygen, which is kind of weird because usually when we think about metals and non-metals, we think about ionic bonding. The bonding is here. Here's the deoxygenated form. Here, this is, and then here's the oxygenated form, O2. Here's another angle of O2 on hemoglobin. And so this is Lewis acid. Oh, here they show it here. But normally we show it a little bit different here. Oh, actually they didn't. I think they showed it correctly. Here we have the lone pair on oxygen coming to attack the Lewis acid iron here. That's going to form a bond. You can see down here. It's a bond. Now, it turns out oxygen's not that great of a Lewis base. They're much better Lewis bases. For example, carbon monoxide. Carbon monoxide is an excellent Lewis base. So if there's a competition between carbon monoxide and oxygen, carbon monoxide wins. In fact, carbon monoxide is such a great Lewis base. It forms quite a strong bond here. And so oxygen forms a weak bond here, so the oxygen can be displaced. But the carbon monoxide is kind of stuck on there. So it's a strong bond. And so that leads to carbon monoxide poisoning, which leads to asphyxiation. You aren't going to get enough O2. And the same thing with cyanide. You know, cyanide is a great Lewis base. And so cyanide can easily attach to the iron. Here, we'll have to settle for this. So you can see the cyanide bonding here. And that's going to prevent oxygen from bonding. Nitric oxide too. And let's see, good Lewis base. Anything with a lone pair that can be, you know, donated. And so probably some structures in here. Here. NO attaching. NO, when it's a ligand, we call it nitrosyl. I mean, ligand, you probably never heard that, ligand. This is Lewis base. It's called nitrosyl. Yeah. Well, nitrosyl or NO or nitric oxide has an important biological role in blood. So I'm not sure if this is the key structure to that or not. I've been following it. Okay, so some more examples. There are lots of examples of biological Lewis acid-base reactions like that. Let's move on. Let's look at pH. You know, when you mix acids and bases with water, it changes the pH. So if you put acid in water, it lowers the pH. If you put base in water, it raises the pH. And we can do some simple pH calculations here. First, we look at the pH scale. pH scale ranges from below 0. So we can have negative, like probably not going to go much beyond -1 here. And above 14, you know, so we'll get to about 15 plus. And so, but the normal range is around 0 to 14. But we could have pHs lower than 0. Negative pHs, those negative pHs, those like in mining, you know, occur. Let's see. The lowest pH found, lowest pH natural water recorded is around -3.6. That's extremely acidic. Negative pHs are extremely acidic, -3.6. This is in California, Iron Mountain, California. That's actually acidic mine waters, you know, so maybe they're using a lot of acid to extract stuff. But they're calling this, yeah, extremely acidic mine waters with pH values as low as -3.6. Profound. And then the pHs can go above 14. Let's look on the other end. What's the highest pH? Highest pH water. A lot of people like to drink, you know, water that's a little higher than 7. So highest pH water recorded. Probably the highest pH ever. This is from geochem. So I guess the geochemists have it, you know, they have the lowest pH, which was that mine, and it looks like they have the highest pH here. These are natural. I mean, natural in the sense that, you know, somebody didn't make this in the lab, although the mine is kind of like a lab in a way. But what was the pH that they got? 12.5. It's still not above 14. 12.6. But it's still pretty high. That's for natural waters. We could get a pH of 14 in the lab easily. Okay. So how do we determine pH and how do we calculate it? Well, pH 7 is what we call neutral, and P pure water. Blood is slightly basic. And so pure water at 25 degrees C has a pH of 7. P stands for power, you know. It's a power function. A power function is the power of the hydronium ion concentration. And so one way of remembering pH is that it's a negative power. pH is equal to the negative power of the H plus concentration. So when we have a pH 7, you know, what that means is the H plus concentration. These square brackets mean a molar concentration. Molar concentration of H plus. that means that the H plus concentration is 10 to the negative 7 power. 10 to the negative 7 molar. That's it. There's 10 to the negative 7 molar is special. It's special because that's pH 7. Now, this is what we call neutral. It's neither acidic nor basic, but it has acid in it. So you're thinking, why is it neutral? The reason is because at this pH, we have the interesting circumstance where the H plus concentration is equal to the OH minus concentration, which is equal to 10 to the minus 7 molar. And so we'll talk about where this comes from in the next slide, but if we have pHs lower than 7, that means we have hydronium ion concentrations greater than 10 to the minus 7. Like if we had a pH of 5, then we have a hydrogen ion concentration of 10 to the minus 5 molar. And so this would be 10 to the minus 5 molar hydrogen ion concentration. pH 7 is 10 to the minus 7 molar. And so if we go to pH 3, it's 10 to the minus 3 molar hydrogen ion concentration. If we go to the pH 0, it's 1 molar. Well, today in lab, I use 6 molar acid. 6 molar acid is going to have a negative pH, like negative 0.5 or so. Let's see. Yeah, that's what the brackets mean. These brackets here mean molar concentration. Molar concentration. That's why they didn't put the units here, because the brackets mean molar concentration. So that's what we got there. Yeah, no problem. And so this is pH neutral, and that's the only place where it's pH neutral was right here. This is neutral. pHs lower than 7 are acidic, and so these are, would be weakly acidic, like milk is weakly acidic. These are moderately acidic. Moderately. This is strongly acidic, like battery acid, strongly acidic, stomach acid, strongly acidic. Moderately and weakly acidic. Here. And so that mine water was minus 3.6, which is extremely acidic. Now, near volcanic vents, they measured high pH water, high pH, like 12, pH 12. pH 12 is like bleach, high pH. And so this is going to be weakly basic, moderately basic, and then strongly basic. And so here, at pH 7, the H plus concentration is 10 to the minus 7 molar, and the hydroxide ion concentration is 10 to the minus 7 molar. So we have this unique situation where both concentrations are the same. At other pHs, it's not that way. Do you see a pattern here in the powers? Take a look at the powers and see if you see a pattern in the powers. One of the patterns is if the H plus concentration goes up. So let's start at 10 to the minus 14 molar. If the H plus concentration goes up, what happens to the OH minus concentration? So as we go up, the OH minus concentration goes down, gets smaller. And so there appears to be a seesaw relationship, and there is. If you look at it, 1 and 13, 14, 2 and 12 is 14, 3 and 11 is 14. The two powers have to add up to 14. And the only place that they're going to be equal is at 7. So we have that. And so let's see more about where these numbers come from. But we could test pH using, this is called indicator paper, like litmus paper. Well, this might be litmus paper here. Red litmus paper turns blue with base. Ammonia is a base. We did this in lab. This is paper that has multiple indicators in here. So we can actually pinpoint the pH more rather than it's acidic or basic. If it's acidic, it's on this side. If it's basic, it's on this side. But with multiple indicators, we might be able to narrow down the pH based on the color here. This is called a pH meter. A pH meter, you just stick the probe. This is called a pH probe. We put the probe in the solution and then just measure the pH. This is a pH of 433, which means it's moderately acidic, like tomatoes. A 6. Tomatoes can be quite bitter. This is coffee. Coffee can too. So when we have pure water, you know, water is an acid and a base. And so if one of these waters acts as the base, let's say this water acts like a base. The bases are proton acceptors. And so let's call this water the base. And the base is going to pluck the hydrogen off here, the acid. And we'll call this other acid, other water acid. And so if there's a violent collision between these two waters, then it can form this. Okay, it can form hydronium. Okay, so this accepts a proton, and hydroxide, this loses a proton. And so going backwards, this would be the acid, this would be the base here. Now at room temperature, at 25 degrees C, you know, there's a curve here, like this. It's called the kinetic energy distribution curve. Which we saw earlier. And this is at 25 degrees C. Most of the water molecules are going to have a kinetic energy around here. Okay, so on the y-axis, we're plotting population. On the x-axis, we're plotting energy. There's a small fraction of molecules which have enough energy to react like this. This is called autoionization. And so it turns out, you know, it's kind of steep because when we look at this, this is weak. This is weak, but hydronium is strong and hydroxide is strong. So we're going from weak to strong. So this is a very steep hill to climb. And so if I had a billion, let's say 1 billion H2O molecules here, about 4 of them might make it up here. And so about 4 H2O molecules can make it up here, but they aren't going to stay there for long because hydronium and hydroxide like to react. You know, they're both strong, so they're going to react and fall back down here, but the next wave is going to bring up 4. The wave is going to be based on this energy, kinetic energy here. And so we end up with a dynamic equilibrium where there's going to be a stable concentration of this up here. You know, and it's going to be very small. In fact, you know, when we're looking at water, we're only going to get about 10 to the minus 7 moles of this per liter. And the same thing here. This is going to be 10 to the minus 7 moles of this per liter. And that's what gives us our pH. When we look at the power is 7. And so the power of the acid, or the H plus concentration, or the hydronium concentration is 7. The negative power is. That's how pH 7. So water has pH 7. This is an equilibrium. So we just have, you know, these waves that keep, in other words, we have these collisions. These collisions can bring it, but these will rapidly go back down. And so what we end up with is something called a dynamic equilibrium. A dynamic equilibrium, we're going to have a stable, you know, amount of hydronium and hydroxide. All right, so let's go ahead and we're going to take a break, and then I'll talk about the calculations next. So let's take a break for a bit, and then I'll start. So when we look at the kinetic energy distribution, there is a small population of molecules, like 4 out of a billion. So if this is 1 billion, then we have about 4 water molecules out here, very thin. And this 4 water molecules have sufficient energy to react like this to form these very reactive, very unstable products. Those very reactive, very unstable products, high energy products, are not going to stay there forever. They're going to come back down here, but the next collision is going to replenish those. So what we're going to have is we're going to have a forward and reverse. So the number of molecules colliding and reacting here is going to equal the number that are going to revert back to water. And so we get a steady state, and the steady state is what we call the equilibrium state. And so this is called an equilibrium reaction, where we have a ratio, you know, of product to reactant. And so this is not like a, you know, this would be a no reaction, you know, in a typical sense. But whenever we have this kind of partial reaction where we can have some reaction occur, this is called an equilibrium reaction. And we handle the equilibrium reaction a little differently stoichiometrically. We do, in order to figure out the stoichiometry, like, you know, how much reaction, how did I know it was 4, you know, out of a billion? Well, I did the calculation. Now, how do you do the calculation for these? Well, you do equilibrium calculations. You don't do standard stoichiometry. Instead of standard. I mean, it's still stoichiometry because it's still, you know, ratios and that type of stuff, but it doesn't go, you know, 100% reaction. And so in standard stoichiometry, we assume that we have a very strong driving force and it goes 100%. And so this is equilibrium type scenario. Okay, so once we have this, in pure water, it's established, it's well established that the concentration of the hydronium and the concentration of hydroxide is 10 to the minus 7 molar and 10 to the minus 7 molar. That's going to give us power. So, for example, the power of the hydrogen ion concentration, which we call pH, is 7. And so this is pH 7. And we also have the power of the hydroxide ion concentration. The power of the hydroxide ion concentration is also 7. Now, there's some relationships here that we want to keep track of. The pH and the pOH together have to combine to 14. So the pH plus the pOH is equal to 14. Now, I got to talk about sig figs, but I'll talk about it a little bit later. And therefore, the pattern I was saying is if the pH goes down, the pOH has to go up. If the pH goes up, the pOH has to go down, you know. And so in other words, there's a seesaw relationship. So this is pure water. In pure water, we're going to have equal amounts. But what if I add acid to this water? If I add acid to this water, it's going to kick the hydronium up. If it kicks the hydronium up, it's going to decrease the hydroxide. This is called Le Chatelier's principle. Likewise, the other thing, you know, if I decrease the hydronium, it's going to kick this forward. We'll talk about that in the next chapter. Okay, there are other patterns too. I could look at the concentrations instead, and if I take the hydrogen ion concentration, the hydronium ion concentration, multiply by the hydroxide, it's going to come out to 10 to the minus 14. This is called KW. KW. This is called PKW. It's the power of KW. So when we look at the power of KW, the negative power of KW is 14. So that's what we have here. Now, to figure out the pH, let's just break it down into equations. If we want the pH is given by this equation. Power functions are given by the negative log of the H plus concentration. And if we want the H plus concentration, we just take the inverse log. This is the inverse log base 10 of the pH. We take the negative pH. And so we could calculate the H plus or the pH. Same thing, hydroxide is equal to this, pOH is equal to that. And so you can do some calculations here. Actually, we'll take a look at the calculations. In the book. Okay. Let's take a look at some chapter 17 type problems. Okay, 1, identify at least 2 of the classical properties of acids and 2 bases. Well, acids are sour. Yes. Well, actually, let's not think about it too much. Classical properties of acids and bases are listed in the introduction as an example of how a property relates to an ion associated. Well, acids are sour, and the properties are they dissolve metals. They change the color of indicators, certain colors. That kind of stuff. Bases too. Let's move on. Distinguish the classical properties. We want the chemical properties. That's really primarily what we're going to focus in on. Bases are bitter, as I said before, etc. Slippery. 3, distinguish between an Arrhenius base and a Bronsted-Lowry base. Arrhenius base is just hydroxide in water. Bronsted-Lowry base is proton acceptor. Yeah, they're in agreement, but Arrhenius, there could be bases that Arrhenius misses because not everything's in water. Excuse me. Explain or illustrate by an example what is meant by identifying a Lewis acid, an electron pair acceptor, and Lewis base. So here we're just looking at an electron pair being donated and forming a bond. This is aluminum chloride. And this has a name I mentioned earlier, tetrachloroaluminate. You discuss these types of things in Chem 1B. It's a Lewis acid base reaction. When dialphyl ether reacts with boron trifluoride, a covalent bond forms between the molecules. Describe the reactions from the standpoint of Lewis acid base theory. From the standpoint of Lewis acid base theory, we use little arrows to indicate. And so here's a lone pair from the Lewis base being donated to the Lewis acid. In a way, it's partially donated. It's not completely. And so it's going to form this bond here. This is sometimes called Lewis acid-based adduct, and so it donates an electron pair to form a bond. This can accept, boron. We have to be able to accept. Sometimes if we donate and there's too many electrons, we have to knock some out by rearranging things. Okay. We're just going to do the odds. Give the formula of the conjugate base of HF. It would be F minus. Conjugate base, that means this acts as the acid. If this acts as the acid, it loses H. If this acts as the acid, it loses H. So HPO42 minus. F minus, HPO42 minus. The conjugate acid, this acts as the base, so the acid would be HNO2. If this acts as the base, this acid would be H3PO4. For the reaction, HS over minus, okay, this is bisulfate and oxalate. This is a bronzite acid-base reaction. You know, the bronzite acid loses a hydrogen to the bronzite base. So we end up with a sulfate and hydrogen oxalate ion. And then we compare, you know, this is acid, this is a base, this is the base, this is the acid, and we compare which one's stronger, you know, bisulfate or bioxalate or hydrogen oxalate. And so we compare. Now, which acid's stronger, bisulfate or hydrogen oxalate? And that'll tell us the driving force. So let's go back here, take a look. And so we have hydrogen oxalate here, bisulfate's here. So we're going from a stronger acid, bisulfate, to weaker acid, hydrogen oxalate. Now these are pretty far apart, and so we have a pretty good driving force for this probably. But there's a chance that there could be an equilibrium situation here, you know, if they're somewhat close. But there's a driving force for this. 3, identify the conjugate acid-base pairs in question 11. Okay, the pairs are this. So if we have this acid and it loses a hydrogen, then it's going to form this base, sulfate. So that's a pair. This is the acid, this is the base, conjugate pair. This is the acid, this is the base. That's another conjugate pair. So they're related. This chart is based on conjugate pairs. Here's the acid, here's the conjugate base. Here's the conjugate base, here's the conjugate acid. The stronger the acid, the weaker its conjugate. The stronger the base, the weaker its conjugate. And so you can see strong, extremely weak. Strong, extremely weak. For the reaction HNO2, nitrous acid plus this C3H5O2, propanoate probably, yields nitrite and propanoic acid. Identify both conjugate acid-base pairs. So here's the acid, its conjugate would be this nitrite. Here's the base, its conjugate would be this. And so this would be a conjugate pair. This is acid base, this is the base acid. Identify conjugate pairs in ammonium. Okay, ammonium would be paired with ammonia, and monohydrogen phosphate would be paired with dihydrogen phosphate. And so ammonium would be the acid, this would be the base. This would be the base, that would be the acid in the pair. Then we can see if there's a driving force. With the driving force, we don't need to do the pairs. We just need to compare the two acids. Now, which is the acid? Well, it turned out H2PO4 minus versus ammonium. That was it. Let's see, H2PO4 minus versus ammonium. Here's a H2PO4 minus, here's ammonium. So it looks like ammonium is weaker. If ammonium is weaker, then what we'll say is that there is no driving force. But it depends on how much weaker it is. If it's only slightly weaker, then that's not such a steep hill. It depends, because we're going from weaker to stronger. And so if we're going from really weak to really strong, then we don't expect any reaction. You know, basically it's too steep of a hill to climb. So if we're going from really weak to really strong, it's too steep. And so we just say, you know, the driving force is downhill, it's reversed. And so it's pretty much no reaction in our. But if it's, you know, if we're going from weaker to stronger, and the stronger isn't that much stronger, then there's a possibility a little bit might react, you know, like anywhere, less than 1%, 2%, 3%, depends on how flat this is, you know. That's all kind of relative. You can't just base it on how many acids are between, because it's not linear, that scale. 17, ammoniums paired with ammonia. Actually, I already did that one. "19, what is the difference between a strong base and a weak base?" According to Bronsted-Lowry's, a strong base can pull off the proton, it's going to go and take off the hydrogen. A weak base doesn't have a strong attraction for the hydrogen. So a strong base in Bronsted is going to have a strong attraction for the hydrogen and pluck it off. So a strong base has a strong attraction for protons. And so they really want a hydrogen ion to pluck it off. List all the following acids in order of increasing strength. Weakest acid first. So looking at this list, I have to say the weakest is water. Maybe the strongest is sulfurous acid. But hypochlorous acid and hydrogen oxalate, I don't know. So we'll just look at the chart. So here's hydrogen oxalate. Where's hypochlorous? Hypochlorous is down here. So hydrogen oxalate's stronger. And so it's going to go water, hypochlorous acid, hydrogen oxalate, and then sulfurous acid. Sulfurous acid is not a strong acid. It's a weak acid, but it's on the strong end of the spectrum. For each acid base given in this section, complete a proton transfer equation for the transfer of one proton. Predict the direction in which a resulting equilibrium will be favored. And so they're calling it an equilibrium. They're calling it equilibrium because we could have partial reaction. The driving force is not so huge, or the non-driving force is not so huge, And so there's a chance that we could have both reactants and products form a stable mixture at the end of the reaction. And so at the end, meaning there's no further change. And so here, this is going to lose a hydrogen. And so we're going to form monohydrogen phosphate and propanoate. And so we need to compare monohydrogen phosphate with the other acid. And so this is going to lose a proton, so it's going to form C3H5O2 minus, and HPO4. It's going to go from 3 minus to 2 minus. And so we're going to compare this. This is the acid here. This is the base, and the conjugate pair is this. So this is the acid here. This is the acid here. This is the base here. So the conjugate, this would be another conjugate pair, but we're comparing the two acids, the acid in the forward direction versus the acid in the reverse. And so this is HC3H5O2, which is actually, it's propanoic acid, but you don't need to know that. Let's see, we should be able to find it on the chart though. It's not going to be on the chart I gave you, but it's on this chart here. It looks like HC3. C3H3O2. I think there's a typo. Here. This must be a typo. It's an extremely odd ratio. But maybe it's okay. What is it? Yes, I didn't mean that. They're thinking I'm talking about acetic acid. That's some kind of chem tool to calculate molar mass. It's a molar mass calculating tool. Acrylic acid, okay. Maybe that's it. But why would they do acrylic acid? That would make sense. Acrylic acid is going to have multiple bonds, and then we can do it. So maybe that's what they're meaning here, but let's go back to this problem. This is not acrylic acid. This is propanoic acid. And so what we're going to do is we're comparing the two acids, propanoic acid versus monohydrogen phosphate. And I would guess propanoic acid is stronger than monohydrogen. Monohydrogen is not very good, so it's 4. We didn't have it in the chart though. Okay, bisulfate and carbonate. This should make sulfate and bicarbonate. And so in that case, I'd go with bisulfate. Bisulfate's borderline strong, and bicarbonate's not that strong. And so we're going to go to sulfate and bicarbonate and compare the two acids. Here, this one's stronger, this one's weaker. So 4. Now we're only transferring 1 proton. If we transferred 1 more proton here, we could form carbonic acid, which would decompose into H2O and CO2. And so it depends. Here, they're telling us transfer 1 proton, not 2. And that's the same thing I said earlier when we were doing these. Carbonic acid and nitrite is going to form bicarbonate and nitric acid. And carbonic acid versus nitric acid is stronger, so the reverse is favored. So nitric acid is stronger, reverse is favored. Nitrite and hydronium is going to form nitrous acid and water. And so this one, the forward would be favored. Hydronium is stronger acid than nitrous acid. So nitrous acid and water, forward. Bisulfate and bioxalate, or hydrogen oxalate. And so here we have a choice. Both of these are amphoteric. Amphoteric means it can react either as an acid or base. And so in this case, we have to go with the stronger. Which is a stronger acid? Bisulfate or hydrogen oxalate. And so we have to consult the chart there. And we look for bisulfate is here. And then we look for hydrogen oxalate, it's down here. So bisulfate is stronger than hydrogen oxalate, which is here. And so this is going to go forward. Or maybe, did I get it wrong? Bisulfate is stronger than hydrogen carbonate or hydrogen oxalate. Now, what are they doing? Oh, oxalic acid, sorry. I forgot to do or finish the problem. So this is actually 2 steps, problem number 33. The first step is, which one is the acid? Okay, which is the acid? Well, both are. So must pick the stronger one. So we picked the stronger one, which was bisulfate. Therefore, bisulfate's the acid, and then hydrogen oxalate's the base. And so bisulfate is the acid, hydrogen oxalate is the base. And so bisulfate is going to lose the hydrogen, it's going to form this, and then hydrogen oxalate is going to gain it. We don't pick this one here. We don't pick this one because the stronger one should act as the acid. Now, if there's not that big of a difference between the two, then it's possible that this one could also react, but we pick the strongest. There's also water in here, so they aren't being complete. If they want to draw every single possible collision, then they have to include the collisions with water. And so bisulfate with water and then hydrogen oxalate with water is going to give us two more equations here. But we just picked the one that's most probable. This one's the most probable here. This is going to be the acid. And then that means hydrogen oxalate, which is also an acid, but both of these are also bases, is going to act as the base. And so the conjugate would be sulfate here, and the conjugate here would be oxalic acid. And then we compare the two acids, hydrogen sulfate versus oxalic acid. Now, oxalic acid is right at the border. You know, hydrogen oxalate is also right at the border. They're very close. And so if we take a look here, here's oxalic acid right at the border, and here's hydrogen sulfate. And so oxalic acid is slightly stronger. Well, if it's just slightly stronger, then that means it's probably equilibrium. You know, we'll probably have a mixture. And so it's probably not as steep as one might expect, you know. And so oxalic is slightly stronger than hydrogen oxalate. So probably a lot can go forward. So the reaction is going to have even though it's favored in the reverse, the reaction is going to have some of this here form. Explain how a strong acid is similar to a strong reducing agent. Well, a strong acid, actually, you know, a base would be better comparison. You know, a strong base wants a H plus, and so a strong base will go and take an H plus off an acid. A strong reducing agent wants electrons, so it'll take electrons from the reducing agent. Let's see what they say. Okay, pretty much this. Reducing agents, this is another way I'm looking at it, but they were asking about oxidizing agent. Oh, here, you're right, the reducing agent. I should read these more carefully. Strong acids lose hydrogen easily, and strong reducing agents lose electrons easily. Reactions are different though. You know. Of what significance is the very small value of 10 to the minus 14 for kW? The significance is only like 4 out of a billion water molecules have enough energy and orientation to react in the ionization equilibrium constant for water. Ionization equilibrium constant, this K is called the equilibrium constant. It's called K. And this is called KW. This is the equilibrium constant for water. It's the ionization equilibrium constant for water. That's what KW is. The very small value for KW indicates that water ionizes to a very small extent. So very few water molecules have enough energy to ionize. And we only get to about 10 to the minus 7 molar, a minuscule amount of H plus and OH minus at room temperature. 39, H plus is 10 to the minus 5. They didn't have to tell us the OH minus because, you know, it's got to be 10 to the minus 9 because the H plus times OH minus is equal to 10 to the minus 14. So minus 5 and minus 9 gives me minus 14. If I look at the power, the pH is 5, the pOH is 9. The pH 5 plus pOH 9 gives me 14. Is the solution acidic, basic, or neutral? This solution is going to be acidic. How do you know? You know it's going to be acidic because the hydrogen ion concentration is greater than the hydroxide. We're always going to have both in any water solution because you can't stop water molecules from colliding. And so an acidic solution is just defined as having more hydrogen ion than hydroxide. A base solution is more hydroxide than hydrogen. What is OH minus? So this is an acid, so there shouldn't be any base, but there is base. The base comes from collisions of water molecules. And so this is the way we do this one here. 0.01 molar HCl is going to give us 0.01 molar H plus. As for every HCl, we're going to get one H plus, which is going to give us 1 times 10 to the minus 2 molar. Now, this is not significant in terms of sig figs, but this is the power. And so the pH is going to equal 2. And then this is 1 sig fig, the coefficient here. And so we call it 2.0. And so the 2 comes from the power here, and it doesn't contribute to sig figs. What contributes to sig figs is the coefficient. And so we have 1, therefore we're allowed 1 decimal place. And so anything preceding the decimal point is not a sig fig. Anything after the decimal point is a sig fig in power functions. In which classification, strongly acidic, weakly acidic, strongly basic, weakly basic, neutral, or close to neutral, does each of the following solutions belong? pH 7 is neutral. pH 9, well, it's greater than 7, so it's basic, but it's not 14, so it's moderately basic. Or what would they give us? Weakly basic. This is not strongly basic. pOH of 3. A pOH of 3 means the pH is equal to 11, because the pH and the pOH have to add up to 14. So if we have a pOH of 3, the pH is 11. 11 is fairly strong, base. So we'd say strongly basic for this one. If the pH of a solution is 8.6, is the solution acidic or basic? It's a basic. pH is greater than 7 or basic. I don't know. They want us to do. Find the pH, pOH, H plus, hydroxide. Find each of the other values. Classify each solution strongly. Okay, so if the pH is 5, then the first thing I'd do is the pOH. So if the pH is 5, the pH plus the pOH has got to equal 14, so the pOH is 9. If the pH is 5, then the H plus concentration is equal to 10 to the minus 5 molar. If the pOH is 9, then the hydroxide ion concentration is 10 to the minus 9 molar. This is no sig figs. Then what? This pH 5 is weakly acidic. Let's do one more. Okay, if the hydroxide is 10 to the minus 1 molar, then the pOH is 1. But there's one sig fig here, or actually there's no sig figs here. And so the pOH, the power of the hydroxide, the negative power of the hydroxide is 1. That means the pH is 13. A pH of 13 is strongly basic. Strong base. Which means the hydrogen ion concentration is equal to 10 to the minus 13 molar. Okay. So if the pOH is 4, then that means the pH must be 10. 10 plus 4 gives us 14. And so if the pOH is 4, that means the OH minus concentration is 10 to the minus 4 molar. And if the pH is 10, that means the H plus concentration is 10 to the minus 10 molar. 10 to the minus 4 times 10 to the minus 10 gives us 10 to the minus 14, which is kW. pH of 10 is like that's moderately basic. You know, they're probably going to pick strongly basic because we don't have choices. And so you could call strongly basic. Yeah. Okay, let's do the next one here. H plus is 10 to the minus 9 molar, and therefore the power, the negative power of that, and therefore the pH is equal to 9. And that's the power. And that means the pOH is equal to 5. That's 9 plus 5 gives us 14. And then that means the hydroxide ion concentration is equal to 10 to the minus 5 molar. pH of 9 is, we'll call it moderately basic or weakly. They're probably going to call it weakly basic. Here. The difference between pH 10 and a pH 9 is, this is orders of magnitude. And so the difference between a pH 9 and 10 is 10 orders of magnitude, 1 order of magnitude, 10 times. And so it has 10 times more basic. The difference between 9 and 11 is 100. So 11 would be 100 times more basic than 9. Or 9 and 12 would be 1,000, 10 to the third. 9 and 12. 12 is 1,000 times more basic. Okay, these ones we need a calculator for. The other ones I could do in my head, but this one is a power of 10, but you look at the coefficient is 2.5. And so it's not so easy to do. And so we need the equation for these. And so the other ones, we don't need a calculator for. This one we do. And so to get the pOH is equal to the negative log of the OH minus concentration. So it's a negative log of 2.5 times 10 to the minus 10. This is 2 sig figs here. And so I need a calculator to calculate that here. And so I'm going to do negative log base 10 of 2.5 times 10 to the minus 10 equals. And so I get a pH of 9.6 here. Now, what do I do about the sig figs? That's 2 sig figs. So this is I'm gonna write this as 9.602, which is gonna round to 9.60. This is 2 sig figs. Because anything to the left of the decimal is what we call a placeholder. It's 9 places out, almost 10 places out. So if the pOH is 9.60, that means the pH is equal to 4.40. You know, because pH and pOH is going to add up to 14. And that means the H plus concentration is going to equal 10 to the minus pH molar, which is going to be 10 to the minus 4.40 molar. Well, what is 10 to the minus 4.4 molar? And so I'm going to do that on the calculator here. I'm going to do the inverse log, so shift log, and then do negative 4.4. That gives me 3.98 times 10 to the minus 5. Molar. And we're allowed 2 sig figs. You know, are we allowed 2 sig figs? Yeah, 4.40. This is 2 sig figs in the power function. Power functions are weird like that. You know, only after the decimal is significant. Preceding the decimal is not. And so we'll round this to 2 sig figs. 4.0 times 10 to the minus 5 molar. That's an example where we're going to have to use the equations and calculators because the math is a little bit harder. The pH meter pictured below is measuring the pH of 0.20 molar ammonium nitrate solution. Ammonium nitrate solution is stable. We don't have to worry about ammonium nitrate solution exploding. No. And so the pH is 4.96. pH 4.96. That means the pOH is equal to 9.04. So 9.04 plus 4.96 should give me 14. That means the H plus concentration is equal to 10 to the minus 4.96 molar. So I'm going to go ahead and do that anti-log here. So I'll take shift log base 10 minus 4.96. 1.09 times 10 to the minus 5. 1.09 times 10 to the minus 5, which is 1.1 times 10 to the minus 5 molar. There are 2 ways I can get the hydroxide. One is by using the same type of equation for hydroxide. So the hydroxide I can get, that's 10 to the minus pOH. So it's going to be minus 9.04. Or I can use KW. You know, KW is 1.0 times 10 to the minus 14, which is going to be the hydronium or hydrogen ion concentration times the hydroxide ion concentration. And so if I take the hydronium and KW, I just take KW divided by hydronium, that should give me the hydroxide. So either way, I'll just do it the first way there. So I'm going to just take shift log base 10 minus 9.04. (9.12 times 10 minus 10 molar). All right, here we're given the hydroxide and hydronium, or no, we're given the hydrogen ion concentration. So we can calculate the pH for this one. Probably do that first. pH, we're going to have to use a calculator for this. Negative log. It's only when the coefficient's 1 we can do it in our head, but it's going to be negative log of 2.8 times 10 to the minus 1. Once we get the pH, then we can get the pOH, and then we can get the hydroxide ion concentration using similar calculations as before. So we get the H plus first. Oh no, this given, the H plus is given. We'll get the pH 0.55, the pOH would be 13.45, and then the hydroxide at the end. Here we're given the pOH. Here we could do this in our head. If that's it, then 6.6 is the pH, 6.6, and then we can calculate the concentrations based on that. Okay, let's look at the general questions here. True or false? All Bronsted acids are Arrhenius acids. That's false. All Bronsted acids are Arrhenius acids. Arrhenius is a little bit more strict in that we have H plus and OH minus in solution. So, but it's aqueous, and Bronsted Lowry acids don't have to be aqueous. And so this is why I disagree with this one here. But it's all right. If you were to take that, like ammonia gas, and put it in water, then it would be an Arrhenius base. And if you take HCl and dissolve it in water, it would become an Arrhenius acid. So that must be what they're talking about. You know, you can make them aqueous if you wanted to, but they can react in the gas phase. So that's why I didn't include Arrhenius there. All Arrhenius bases are Bronsted Lowry bases. Yeah. But not all Bronsted Lowry are Arrhenius bases. Anyway, let's get it. Let's pass this. We're just, you know, most people don't worry about Arrhenius. Most people are worried about Bronsted and Lewis. And so we don't really use the Arrhenius definition much. Bicarbonate is capable of being amphoteric. Yeah, it could lose a proton, it could be an acid, form carbonate, or it could gain a proton and form carbonic acid. So that's true. HS minus is the conjugate base of sulfide. No, that's got to be the conjugate acid. Sulfide's going to be the base, and it accepts a proton to make the conjugate acid. That's false. If the species on the right of an ionizing equilibrium are present in greater abundance than those on the left, the equilibrium is favored in the forward direction. Yeah, yeah. If the products are more favored, then it's forward reaction. This is downhill in the forward direction, so the products are favored over the reactants. Ammonium cannot act as a Lewis base. That's true. Ammonium can. Now, why can't it? Well, it's already maxed out. It doesn't want any more hydrogens because there's no electrons to bond it. And so if we have ammonium here, just do the Lewis structure. And we try to react it with acid, call this the base. What are we going to attach the acid to? There are no lone pairs or anything to attach it to. And so there's no reaction. So Cannot act as a Lewis base. That's true.
Professor,
Yeah.
it's break time.
Okay. All right, let's go ahead and we're going to go for a break here. We'll stop it here. I'm going to pause the recording. So ammonium can't act as a Lewis base because there's no place for the hydrogen ion to go. And so if it did act as a Lewis base, then what we'd form is we'd form NH5 2+. But when you do the bonds, there aren't enough electrons because NH5 2+ would have 2, 4, 6, 8 electrons altogether, 5 from nitrogen and then 5 from hydrogen, minus 2 from the +2 charge. So that gives us 8 electrons. 8 electrons we can only form 4 bonds with. And so there's no electrons to form a 5th bond here. And so that's why it doesn't happen. Weak bases have weak attractions for protons. That's true. You know, strong bases have a strong attraction. Weak bases will have a weak attraction. The stronger the acid and the stronger the base are always on the same side of a proton transfer. Yes. Yeah. It always goes strong, strong to weak, weak. This is because of the conjugate relationship, or weak, weak to strong, strong. True. A proton transfer reaction is always favored in the direction that yields the stronger acid. That's false. We always want to go to the weaker, you know, we want to go from stronger to weaker. This is uphill, going stronger, so it's false. A solution with a pH 9 is more acidic than one with a pH 4. No, it's more basic. False. A solution with a pH 3 is twice as acidic. No. There's 3 orders of magnitude. So the difference between a pH 3 and a pH 6 is 1,000. So this is 1,000 times more acidic than this because it's powers of 10. Each unit is a power of 10. These are power functions. So, a pOH of 4.65 expresses the hydroxide ion concentration of a solution to 3. No, power functions are weird because everything after the decimal is significant. Everything preceding the decimal is insignificant. So this is only 2 sig figs, not 3 sig figs. So that's false. Theoretically, can there be a Bronsted-Lowry acid-base reaction between hydroxide and ammonia? Theoretically, there can be, but there might not be any driving force here. Ammonia is actually amphoteric. And so the reaction could be like this, where hydroxide plucks a hydrogen off there to form water and NH2 minus. NH2 minus is amide. And so this is the base. And ammonia is usually thought of as a base too, but in this case, it's going to be the acid. And then going forward, this is the acid, this is the base. And so speaking of acids, which acid is stronger? Water is a stronger acid. Ammonia. Speaking of bases, which bases? Amide is stronger than this. And so, yeah, theoretically, there could be a reaction here, but the driving force is reverse, you know. So this is kind of a climb here. You know, theoretically, we might be able to form a little bit of amide because it goes uphill a little bit. The bulk of it's going to be down here. And so they got water and amide. I picked the stronger, the stronger acid is going to be the acid, and the stronger base will be the base, so hydroxide. This reaction is much less probable here. This one. They're showing all the variations. If they're going to show all the variations, they need to show all the variations, including water. I'm picking just the most probable reaction. The most probable reaction is not favorable, then the less probable reactions are going to be even less favorable. And so I only show one, the most probable, the strongest acid reacting with the strongest base. That's going to be the most probable, but it needs a driving force. In this case, it didn't have a driving force, so that's why even picking the strongest acid and the strongest base didn't result in a reaction. Explain what amphoteric means. Give an example of amphoteric substance other than water that does not contain carbon. Well, there are lots of examples, you know, but water is unusual. Water is unusual in the respect that it can go either way. You know, water can easily be an acid or just as easily be a base, but other amphoteric species are biased. So for example, HSO4 minus, this is much better acid than a base. In fact, this is close to a strong acid, but as far as a base, it's negligibly weak. That's HSO4 minus versus hydroxide. Hydroxide is a much more powerful base than an acid. This is an exceptionally weak acid. You know, it could lose a proton to form oxide, but it's a powerful base. And so that's the situation. If we don't have water, then one side's favored over the other side, you know. Sometimes it's not huge, the difference. Sometimes it's huge, the difference. Where it's not huge is when it's kind of in the center or close to it. So like hydrogen oxalate, it's kind of a mid-range acid, hydrogen oxalate. And then let's take a look over here. Hydrogen oxalate is kind of a mid-range base, you know. So let's see. Monohydrogen phosphate. Monohydrogen phosphate, let's go here. Kind of weak acid, but it's an okay base. So there's a preference, one way or the other. Sometimes it's big, sometimes it's not so big. Sorry for that, the noise. It's pretty noisy here today. Very small concentrations of ions other than hydrogen and hydroxide are sometimes expressed with P numbers. Calculate PCl in a solution. Well, whenever we have a power function, it's always the same. It's the negative log. And so a power function is just for many different things. So P, this would be the power of the chloride ion concentration. It's going to be the negative log of the chloride ion concentration. It's going to be the negative log of this. This is going to be around 8. 8 to 7, 7 to 8. It's a 7 point something. Yeah, 7.126. We could just punch it in the calculator. We could get that. Can a substance that does not have hydrogen ions be a Bronsted-Lowry acid? No, Bronsted-Lowry acids are hydrogen donors, so no, it can't. No, Bronsted-Lowry acids are proton donors. Why do you suppose chemists prefer the pH scale to expressing hydrogen ion concentration? In other words, what is the advantage of saying pH 4 rather than H plus 10 to the minus 4? It's just easier. Less writing, less work. Simplicity. That's why. What is the bromide ion concentration in a solution if a report gives the P bromide? A bromide ion concentration is going to be 10 to the minus 7.2 molar. And so it's the anti-log. This one we have to punch in our calculator. So we punch that in our calculator. Get this. How many sig figs? This is allowed 1 sig fig, so they just rounded it to 1 sig fig. Here. Suggest a reason why the acid strength decreases with each step in the ionization of phosphoric. Yeah, this one has the most hydrogen, so it's going to lose it the easiest. This one has fewer hydrogens, and it also has a negative charge. The negative charge makes it harder for an H plus to leave. This one has a 2 negative charge. And so the more negative this becomes, the harder this is to break free. Yeah, they're selling double minus. This is a minus charge, single minus charge. You know. This is electrical attractions. Theoretically, can there be a Bronsted-Lowry acid-base reaction between sulfate and fluoride? No, impossible. There's no hydrogen to transfer. Theoretically, there could be a Lewis acid-base reaction between these two, but not a Bronsted. There's no H. 73, sodium carbonate is among the most widely used industrial bases. How can it be a base when it does not contain hydroxide ion? Bases just have to accept protons, that's it. And so if we have a carbonate here, CO3 2 minus, it just has to be able to accept a proton. So it could accept 1 proton, it'll make bicarbonate. It could accept 2 protons. And so if it accepts 1 more proton here, it'll form carbonic acid. And so it's a base. It's a base because it can accept a proton. Now, it can also take a proton from water. So if we have carbonate in water, the carbonate can pluck a proton off water to form bicarbonate and hydroxide. The hydroxide is going to change the pH of the water because this will change the pOH, which is eventually going to change the pH. So adding carbonate to water makes the water basic. It adds hydroxide, which is base, to the water. But this is not favored. When we look at it, this is the base here, this is the acid, this is the acid, this is the base. We're going from weaker base and weaker acid to stronger acid, stronger base. And so really the driving force is the reverse. However, it's not incredibly steep. And so a small amount of hydroxide can form. Most of it will stay as reactants, but a little bit of hydroxide will form in this, and that little bit of hydroxide will change the pH. Carbonate's called a dibasic base because it can accept 2 protons. Here it's the first proton. That's what we look at usually and then stop there, but it's dibasic. It can accept another proton here from carbonic acid. Carbonic acid is not a base at all, but bicarbonate is. It's both an acid and a base. Non-metal oxides can react with water to form acids. For example, carbon dioxide reacts with water to form carbonic acid. Clear that. And so this is an example of a Lewis acid-base reaction here, CO2 and water. It's a Lewis acid-base reaction. The Lewis acid is an electron pair acceptor. The Lewis base is electron pair donor. So water is the donor, CO2 is the acceptor. When we have Lewis acid-base reactions, it's best to look at those using Lewis structures. And we often look at those mechanistically. So CO2 and water mechanism. When we do this mechanistically, we do little drawings like this. These are Lewis drawings here. And this is called a mechanism. Okay. So here we have water and then CO2. And the reason CO2 is acting as an acid here is because the carbon The carbon's pretty positive here. And there's a delta plus on the carbon. Let me put that here. And this oxygen is a delta minus. So we got this attraction going on here. And then we got a lone pair here, but carbon's already got an octet. It doesn't want any more. But what happens is this electron pair forces its way in here, but it's going to have to kick these out. Otherwise, we got, you know, carbon can't have more than an octet. And so the max number of bonds carbon can have is 4. If I try to make 5 bonds, it's not going to work. And so here's that bond coming in, but what happened is that double bond broke, so now it's a single bond, and then that bonding pair becomes a lone pair, so we had 2 lone pairs here, now we have 3 lone pairs here. And we form this. Well, this is fine, everybody has an octet except the formal charge. The formal charge is not so happy. But they're vibrations, and so if this lone pair on this oxygen gets pushed over here into the hydrogen, there's a big vibration, you know, kinetic energy, big vibration. This oxygen, which is quite basic, can pluck this hydrogen off. That would be a Lewis acid base type reaction, electron pair donor, electron pair acceptor. But this hydrogen doesn't want to form 2 bonds, and so it has to break one. So it's going to break this bond here, and this bonding pair will turn into lone pair. And so this isn't as stable as this because the formal charges here, there are no formal charges here. And so what we do is we go from water and CO2 through this intermediate stage here to carbonic acid. This would be carbonic acid here. Then carbonic acid is going to decompose into CO2 and water. That's the favored direction, but you know, even though that's the favored direction, a little bit of carbonic acid can form because you can't stop the collisions. And so the favored direction is carbonic acid decomposes into CO2 and water. But this can occur because you can't stop the collisions. Collision can occur, form this, and it can rearrange to this or go back to that. This is called a mechanism. So for Lewis acid base reactions, we do this. We do it mechanistically. And that means we have to draw out all the Lewis structures, and then we have to see, you know, how we can rearrange the electrons to form bonds and break bonds and that kind of stuff. We look for delta pluses and delta minuses. Delta plus are acid sites. So H acid site, acid site, acid site. Delta minuses are base site. So base site, base site, base site. There's another possibility here, and that is this oxygen attacks this hydrogen. And so this oxygen attacks this hydrogen. That's another possibility, but that one dead ends. Whereas this one goes on, you know. I missed the question. What acid forms as a result of the reaction of sulfur trioxide and water? So we have sulfur trioxide and water. We could do this mechanistically, but we can also just do it based on pattern. CO2 in water forms H2CO3. So SO3 in water is going to form H2SO4. We're going to add 2 hydrogens and an oxygen to that. H2SO4, sulfuric acid. 75. Metal oxides can react with water to form bases. Write an equation to show how calcium oxide can react with water to form base. All right, this is also a Lewis acid base reaction, but this one could also be Bronsted acid base. I did this one in class, but let's see if I have it, if I can find. Mechanism. Well, there's not a good one here. I wrote it on the board in class once. It's probably magnesium, I know, is sitting there. I saw it there. Maybe I did magnesium oxide. can do calcium oxide like this. We're going to make the crystal lattice calcium oxide. Just 1 second. It was just a little problem there. Well, anyway, we know oxide's a powerful base, but here it's locked in an insoluble lattice, so it's not nearly going to be as powerful. If it were aqueous, then it'd be quite powerful, and so this lattice is going to extend. And so calcium oxide is a weak base, even though oxide itself is a strong base, you know, because it's stuck in the lattice here. But water can be here, and so if the water collides like this, then we can do this mechanistically, or we could do this Bronsted. Bronsted is just a proton transfer here. This one, mechanistically, you know, we can think of this lone pair here. This is the electron pair donor, so this is the base, this is the acid, but there are too many bonds to hydrogen, so these have got to leave here. And so what we're going to end up forming here is this oxide is going to get converted into a hydroxide. Calcium hydroxide is soluble, so this one will just be. And this water will also get converted into a hydroxide. Like that. And so calcium oxide ends up forming calcium hydroxide. Is the net reaction for that. So let's take a look at that reaction here. Calcium oxide plus water ends up forming calcium hydroxide. This is a Lewis acid-base reaction, or Bronsted. In this case, Bronsted works. With CO2, Bronsted's not going to work. But for this one, Bronsted will work because water is the acid. Nitrogen dioxide, well, actually, nitrogen monoxide or nitric oxide is emitted initially, and then the nitric oxide is oxidized by air to nitrogen dioxide. So eventually, nitrogen dioxide ultimately is produced in the automobile exhaust. Explain how this can contribute to acid rain. And well, nitrogen dioxide can react with, nitrogen dioxide is a Lewis acid. And like CO2, it can react with water. So if NO2 reacts with water, I'm not going to do this one mechanistically. I'm going to do this one based on patterns. And based on patterns, this should form HNO3. HNO3. To balance things out, so we have two NO2s reacting with the water. One's going to form HNO2, nitrous acid, and nitric acid. The nitric acid is going to cause acid rain. It is also possible for the nitrogen dioxide to combine with oxygen and water in the atmosphere to form nitric acid. So it's NO2 with water and oxygen in air to form nitric acid here. This is a redox. So both of these are redox reactions here. and more kind of skeletal redox because it's a bit tricky. All right, those are some acid-base problems. Session timed out. I didn't make a PowerPoint for chapter 18. Forgot to do that. Chapter 18 is kind of like two different topics here. One is equilibrium, you know, the equilibrium reactions we've been talking about, where there's some kind of mix of both products and reactants at the end of the reaction, what we call equilibrium. The other is kinetics. You know, kinetics is how fast things occur. And so, let's take a look here. And so, equilibrium. Then collision theory is more kinetics. Molecular collisions, kinetics. Rate of reactions, kinetics. Temperature is kinetics. So this is all kinetics. And so 18.2 to 18.4 is kinetics, 18.1, 18.5, 18.6, 7, 8, etc. Equilibrium. And so we're going to take a look at these here. It's 4 o'clock. But let's take a break now, timing wise. And so we're going to go on a break, even though it might not be exactly break time, but we'll call this break. No. Okay, I'm gonna pause the video right now. Resume the recording. So chapter 18 deals with chemical equilibrium. We talked about equilibrium before with vapor pressure and solubility. Just one second. You have a question? No? Just one second. Sorry, just checking if they needed to. All right, so this is going to be equilibrium in terms of reactions, chemical change rather than a physical change. So that's one of the characteristic differences here. Chemical change, reversible. Whereas the earlier equilibrium we were looking at are reversible physical changes here. And so let's take a look at, well, we already looked at some, but we use this double-headed arrow, not double-headed. A double-headed is for resonance. This is a double arrow, which is different than a double-headed arrow for chemical reactions. And so here's the forward reaction. This is a precipitation reaction. This is some calcium with some bicarbonate to precipitate out calcium carbonate here. Looks like there's some CO2 being generated as well. There's two reactions going on here. Oh, this is an odd reaction. Well, anyway, this is a mix of reactions. So this is not a typical reaction that we would see. It's just because they have some excess bicarbonate. So this is something that could happen in this particular reaction. But if there's acid, that acid would attack the calcium carbonate as well, dissolve that. But anyway, it's a dynamic equilibrium. So let's just take a look at some other reactions. But before we can get to the other reactions, this is why I say there's kind of like two chapters in one. So on the one hand, we're talking about the dynamic equilibrium. On the other hand, they're talking about kinetics, you know, collisions and that kind of stuff. And So both are important, but they're kind of two separate topics here. And I was talking about the waters. Why are the two waters reacting? And so we're going to switch gears here and talk about kinetics, and then we're going to come back to the equilibrium reaction. And those are reacting because you have a violent collision between two water molecules, and that can create, hydronium and hydroxide, or pH in water, neutral water here. So this is an example of collision here. And this is an example of a successful collision. So you take a molecule of this and a molecule of this, and they collide successfully to make these two new molecules. This looks like two elements to combine to make a compound. So it could be like hydrogen and chlorine to make two HCl's here. But the hydrogens and chlorines have to collide in the right orientation. So this is actually kind of the right orientation, but not the right energy. This is kind of the wrong orientation here. And so we need two things. We need the right orientation and right energy. So here they manage to collide, but not react. Here they might have enough energy, but they're not in the right orientation to make the HCl's. And so this kind of collision theory right there. So again, we need the right amount of energy. So let's take a look at this video.
For two molecules to react, they must collide. If an ozone molecule and a nitrogen monoxide molecule meet without enough energy to overcome their bond energies, a reaction does not occur, and the molecules separate without reacting.
So we need these two to collide with enough energy to break bonds and form new bonds. And so it turns out that, what proportion of molecules have the right orientation, the right energy, and it turns out it's a small fraction. If every single collision resulted in a reaction, then we'd have rates that are huge, like 1 million moles per minute, reacting. The reactions would be quite explosive, although we can still have explosive reactions, even at lower rates. Okay, collision theory effects of molecular orientation. So we need the right amount of energy so they don't just bounce off, and we need the right orientation.
If the two molecules collide with sufficient energy to overcome the activation barrier, but with an orientation that does not allow new bonds to form, no reaction takes place. The molecules will separate unreacted.
Okay, so here they're saying they have enough energy, but their orientation's wrong. And so let's take a look at this collision here.
If a collision occurs between the two molecules with sufficient energy and the proper orientation, then a reaction can take place to produce molecules of O2 and NO2.
So this reaction here that they were showing is the reaction between, I thought it was between ozone. Yeah, it was actually.
If a collision occurs between the...
This is ozone here. This is nitric oxide to form nitrogen dioxide and oxygen gas. Ozone's another product that's unstable. It's very reactive. It's another product of smog, the chemical smog. And so those videos were just illustrating the importance of orientation and energy. And so we're going to look at energy changes during a collision. So we have to have enough energy. And what we're going to do is we're going to track these reactions by this diagram. This diagram is called a reaction progress diagram, reaction progress or reaction profile diagram. And so what it does is it tracks like A2 and B2. A2 and B2 needs enough energy in the collision. So that's what it's climbing. It's climbing this hill here. If we don't have enough energy to make it up the hill, then we're going to just go back down the hill, revert back to reactants. And so we have to have a forceful enough collision to make it over the hill. Now, how much energy is that? Well, the height of this hill is called E sub A. E sub A is called the activation energy. And so when we have a collision, how much energy do we need? We need the activation energy worth. Anything lower than this, it's not going to react. Not only that, we need the correct orientation. So not all the molecules that have enough energy to make it to the top will react, because they'll just go back down here because they aren't oriented correctly to form the product. Now, once we make it to the top of the hill, there are two things that can happen. It can go backwards and reform reactants, or it can go forward and form product. If it goes forward here, now this is favorable. This is exothermic. It's going to release energy. And so this is exothermic down here. But the net energy change is going to be this. You know, it's not going to be all energy going downhill here, because we had to expend this much energy going uphill. And so the net energy is delta E. This is the net total energy. And between the reactants and the products is this. What we're missing is this. This is the kinetics part of this. The kinetics part is, this is telling us how fast the reactions go. How fast the reactions go depends on how big this hill is. If this hill is very big, then it's going to be a slow reaction. We can speed it up by increasing the temperature and get more molecules, you know, climbing over the hill. That's one thing. But that's it. And then, so this is the kinetics part. And then when we look at the initial state, that is the products, and compare it to the reactants here. I mean, excuse me, this is the reactants, this is the products here. When we compare the reactants to the products, this is called the thermodynamics of this. Thermodynamics. And so when we're looking at exothermic or endothermic reactions, we're looking at this. This is the thermodynamics. This energy change between the initial and the final is the thermodynamics part. And this E sub A is the kinetics part, you know, how big that hill is. If the hill is very small, then the reaction is very fast. If it's very big, the reaction is slow. And the reverse reaction can also occur by going backwards here. But when you look at the reverse, it's an even bigger hill to climb. So it's really tough reaction. All right. This is called a transition state complex. The transition state complex is right at the top here. And what we have here are these bonds are breaking here. This bond's breaking. And these bonds are forming here and here. And so we have bonds forming here, and then bonds breaking here. Yeah. And so transition state, we don't actually, and transition state is, you know, at the top of the hump here is how, you know, how much energy it takes to form this transition state, which can drop into products over here. Normally when we're doing thermo, we only look at the reactants and the products. This is like the flame, you know, when you have a flame, there's a whole bunch of stuff going on inside the flame. But we don't pay attention to that, because when we think about the flame, we just think about methane and oxygen going to CO2 and water. We don't think about all the species in between. Well, this is thinking about the species in between here, because this is mapping out what's happening when we're going from reactant to product. And so kinetics and thermodynamics, normally these are taught in two separate chapters, but our book teaches it in one chapter here. This is just making it over the activation hump. It's a barrier, energy barrier, because you have to have enough energy to make it over that barrier. It's going to limit things. So when we're looking at temperature, one thing you can do to get more molecules to make it over that hill is give them more energy. If they have more energy, then they can make it over the hill easier. And so this is looking at the kinetic energy distribution at two different temperatures. The blue one is at 25 degrees C. It's going to be the same population. And so the area under the curve is the same for the blue and the red. The red one is at 75 degrees C. And this cutoff here is the minimum energy required, you know, for reaction, which is the activation energy. And so at lower temperatures, the fraction's smaller. At higher temperatures, the fraction's larger, because the red's going to encompass the entire area under the curve here, all the way to the bottom here of that. And so the red is going to have a greater proportion of molecules with enough energy. You can draw that out here. So the red's going to be this entire thing here. And so increasing the temperature is one way to get the reaction to go faster. Decreasing the temperature is, you can slow down reactions, fewer molecules will have enough energy, and increasing temperature will speed up the reaction. So let's take a look at these videos here.
Water sits in a flask at room temperature. A vacuum pump is started and connected to the water flask. The water boils even though no heating has occurred.
Here they're lowering the activation energy. And so, and this is not so clear in this particular video. And I don't know why they started with this particular one, but in this one, normally we need like 1 atmosphere. We need 1 atmosphere vapor pressure to boil water. But if we hook it up to a vacuum pump and we can get a much lower pressure, then you're lowering the activation barrier. And so that makes water a lot easier to vaporize. So the curve stays the same here. It's just under normal atmospheric pressure, the molecules have to have enough energy to overcome 1 atmosphere of external pressure. But if you lower the external pressure, then the molecules don't have to be as energetic. And so by changing the activation energy, we can get this to speed up, the reaction to speed up here. And so that's what they did here. The activation energy used to be here, now it's here with the vacuum pump. And so this is just changing, basically this video is just showing changing the activation energy by providing, this is what catalysts do. Catalysts speed up the reaction, not by changing the temperature. Catalysts just make it easier for the reaction to occur, just like a vacuum pump will make it easier for boiling to occur. So what catalysts do is they'll lower the activation barrier by usually providing an alternate mechanism. And so catalysts and enzymes will do this essentially. Okay, if we don't have a catalyst, then temperature can do the same kind of deal.
If we pour equal amounts of hot and room temperature bleach into separate beakers of colored water, we see that the hot bleach on the left destroys dye molecules more rapidly than the room temperature bleach on the right.
So yeah, the hot bleach is working by this method here. The hot bleach is because the activation energy is not going to change. It's just bleach and food color. And so the hot bleach is going to have more energetic, actually a greater proportion of energetic molecules that can react. And so. And this is a kinetic energy distribution curve. Thermal distribution curve, Maxwell-Boltzmann distribution curve. Now, changing the activation energies, what a catalyst does, a catalyst makes the reaction easier, weakens the bond or does something like that. And so the effect of catalysts speed up reactions on both ways. Catalyst is just going to lower the hill. That's it. And so here's an example of lowering the hill here. Actually, this is not going to come out. Oh, maybe it did come out all right. Here, without catalyst, we have to climb this big red hill. But if we add a catalyst in there, then it provides an alternate path around. So we don't have to go all the way up this hill. We can go this, and all of a sudden the proportion of molecules are going to be much greater. The activation energy shifted to lower energy. The reaction is going to proceed much faster. Both forward direction and reverse are going to have lower activation energies. Is this one showing? So this is showing the shift. Oh, actually, it's the same diagram. This one's showing the shift. Without catalyst, the activation energy is kind of high, way up here. So this is the fraction that can react. With the catalyst, the activation energy, the hill's been lowered, so a lot more can make it over the hill. And so all these out to here, anything above here will be able to react with the catalyst. Here. This is hydrogen peroxide. Hydrogen peroxide decomposes rapidly with a catalyst, you know. And so here is, you know, normally hydrogen peroxide bubbles slowly, but this is bubbling rapidly. It's getting very hot. Steam is boiling essentially. I guess this beetle uses, you know, the bombardier beetle. The beetle has a gland that produces hydrogen peroxide, which is mixed with a substance that catalyzes its decomposition when it becomes necessary for the insect to defend itself. A biological catalyst, an enzyme. Enzymes are biological catalysts that speeds up the decomposition. Hydrogen peroxide solution occurs naturally in potatoes. And so potatoes will speed up hydrogen peroxide decomposition as well. Hydrogen peroxide decomposes into oxygen and water. This is a distillation apparatus. This is just separating crude oil into different components, you know. And so this is distilling. And so the most volatile ones get to the top. The least volatile ones stick to the bottom. So this is called fractional distillation. And you get fractions. So this is a way of separating mixtures by distillation. Catalytic cracking is also getting reactions going. And so as well to get, let's see, this is breaking up the big molecule here into smaller molecules is with a catalyst here. Cracking, I guess. It's breaking up the smaller, breaking up the big to smaller. So far we've encountered two ways to speed up reactions. Oftentimes we're interested in speeding up slow reactions. One way is to use a catalyst and they'll change the activation energy. The other way is to heat it up, you know, they'll change the population. Another way to impact rates of reaction is by concentration. You know, you make it more concentrated, the reaction goes faster because there are more collisions. You know, the more concentrated. This is glowing splint in pure oxygen. You know, this is just a piece of wood, and you put that in pure oxygen, it reacts much more violently, much more vigorously. I wish they had the video of this one, but they don't. In air is only 20%, 21% oxygen, so a glowing splint just has a nice little flame. This one's like a sparkler. Okay. And so concentration, you know, the more concentrated, the more collisions, the faster the reaction takes place. So that's concentration. And so that's a little bit about kinetics. Now we're going to go back to equilibrium. So we're talking about equilibrium earlier. Equilibrium is when we have, you know, when it's not, the seesaw's not tilted so much, you know. So for example, equilibrium happens when, you know, like for example, if it's steep uphill, it's like a vertical climb up a cliff, then this is pretty much no reaction, right? The driving force is the reverse. So this is a reactance of the products that's unfavorable in the forward, but in the reverse, it's favorable. And so backwards, going backwards here. Or if it's steep downhill, you know, then we expect a reaction because we're going to have driving force. Driving force is present, going from reactant to product. But, you know, if it's not tilted so dramatically one way or the other, then we can have both, you know. What we can have is a little bit of the product forms here, and over here, a little bit of the reactant remains here. And so a little bit of reactant remains because we favor product here, and we favor a reactant here, but a little bit of product can form because it's not so steep. This is the thermodynamics thing. You know, we don't care how fast it takes. You know, eventually this is where it should end up. I'll give it enough time. We need time, of course, because the forward reaction takes place. As the forward reaction takes place, we build a product. And initially, the product is not, nothing's really happening. And then, well, actually, this is a reactant. As the forward reaction takes place, we consume the reactant. So reactant concentration is going down. Or this is forward rate. Yeah, forward rate goes down. And the reverse rate is going to kick up, you know, as the concentration is changed. Okay, that animation is not working. So that's just achieving equilibrium. We saw the same diagram in vapor pressure. This just looks like the vapor pressure thing. You know, eventually, once we hit here, this is no change. So this is the end of the reaction, but we're going to have a mix of reactants and products. Le Chatelier's principle. Le Chatelier's principle says once we establish an equilibrium, we can upset it or perturb it. And this is Le Chatelier here. And so what do I mean by perturbing? And so let's say we have an equilibrium here that's established. If we end up adding more HI, that ruins the equilibrium. And then what happens is the equilibrium will try to reestablish itself by, you know, decreasing. If we have too much product here, it'll try to decrease the product and increase the reactants. And so it'll try to achieve a new equilibrium condition. And so let's check out this video here.
A hydrochloric acid solution is added, and the solution changes color to blue. Water is then added, and the original pink color returns.
So what they're doing here is they're just pushing the reaction forward or reverse, you know, depending on.
The beaker contains a solution of cobalt 2 nitrate. A hydrochloric acid solution is added, and the solution changes color to blue. Water is then added, and the original pink color returns.
So this is more Chem 1B. When the chloride and cobalt interact, it forms a blue complex, but we can you can add water and revert back by kind of offsetting things. And so the way I usually do Le Chatelier's is something like this here. Let me just do it. So Le Chatelier's I think of as like a bathtub, you know. And it doesn't matter which side's favored. And so, for example, we could say the products are favored. And so if I had like a weird tub like this, or here's my reactants, here's my product. And in this case, the products are favored. So this is going to be filled with water. And most of the water is going to be on the product side here. Like that. And so the scenario would be like this, you know. The scenario would be like if we had some kind of ramp like this. And then the water is going to be mostly on the right side, you know. Water is mostly, water is mostly on the right side here. But a little bit of water will make it up to the left side. There's waves or something. There's some kinetic energy. So there's waves. And so that would be the scenario here. A little bit of water on the left side, the reactant side, most of the water on the product side because it's the downhill direction here. Now what can happen is this. If I add more reactant water, so if I pour water on this side, what's going to happen? Well, the water is going to drain out here and it's going to fill this. But it's also going to make a little bit more water here. So both levels rise. So if I add water here, both levels rise, but I have net water moving this way. If I add water to this side, then this side has too much water and the water is going to go this way. And so that's called a perturbation. So if I add water to this side, this level's too high. And so it's got to shift right. That is, some of the water has to drain out and fill this side. If I add too much water on this side, then it's going to drain, it's going to go and push the water to the left. And so that's called a shift. And it doesn't matter, you know, which side is favored, you know, we're going to get a shift regardless. And so here's a case where the reactants are favored, you know, and so most of the water is on the left side here. Here's a side where it's more 50-50, you know. And so there's not a huge difference between reactant and product in terms of stability. And so here it would be like this, where most of the water is on the reactant side and a little bit of water makes it to the product side. Here it's more flat. And so we're going to have water on both sides, you know, the left side over here and the right side. So this is a typical Le Chatelier's problem here. I don't know which side's favored, you know, if this side's favored this side, but, you know, this is an equilibrium. So equilibrium, both sides are present. One side's usually favored over the other, or they're about 50-50 maybe. But in this case, there's some kind of ratio here. And let's say we've established the equilibrium. Well, if we add more N2O4, it's got to shift it to the right, you know, because too much reactant now. It's going to shift the water to the right. And so adding N2O4 results in forward reaction. Removing N2O4, so if we suck water out of this well, then the water is going to move left in order to compensate. So reverse here. Adding NO2, so if we add NO2, we add water to the right, it's going to shift it to the left. So reverse. Removing NO2, well, if we take out NO2, we take out water off the right, it's going to shift it to the right and forward. So that's called Le Chatelier's perturbation. In terms of concentration, we also have a volume and a pressure effect. Pressure is the same thing. Pressure and concentration are directly proportional to one another. And so if I change the pressure of the gas, let's say I add more NO2, you know, so I have a higher pressure, then that will shift it to left. Or if I add more N2O4, that's going to increase the pressure of N2O4. If I increase the pressure of both of these, then it depends on which one will have a greater impact. And so we can look at that in terms of a volume effect. You know, one way of increasing pressure is decreasing the volume. And when we decrease the volume, it's going to favor the side with fewer moles. And when I increase the volume, it favors the side with more moles of gas. And so when I look at N2O4 here and NO2, there's 2 moles of gas here. So smaller volumes favor the left, bigger volumes favor the right, because I just have twice as many particles of gas on the right than I have on the left. If it's equal, let's say I'm going from 2 moles to 2 moles, then it doesn't matter. Volume has no impact. And so expanding this will favor the right NO2. Decreasing the volume favors the left N2O4. It's hard to see in that. Let's see this.
A sealed flask contains 3 molecules of nitrogen dioxide for every 1 of dinitrogen tetroxide, and the system is at equilibrium. If we then transfer the mixture to a flask with a smaller volume, NO2 molecules convert to N2O4 molecules, resulting in a net decrease in the number of molecules. In this way, the system compensates for the decrease in volume by a decrease in gas pressure.
Okay, the reverse, they should have showed the reverse one too. Would have been good. Where you increase the volume and then you can increase the number of molecules. So we'll look at the end of the chapter ones. These in the chapter ones you can do here. Temperature is also going to have an impact. Temperature actually changes the balance, you know, it changes the size, the product and the reactant. And so it changes the actual ratio of product to reactant. And so temperature is going to favor the endothermic direction, you know. And so if we look at this reaction as written here, this is actually exothermic. So if I increase the amount of heat, that's like adding product, which is going to shift it left. If I decrease the amount of heat, then I'm decreasing the amount of product, which is going to shift this to the right. And so take a look.
In a sealed flask, we have a mixture of dinitrogen tetroxide, a colorless gas, with the brown gas, nitrogen dioxide. When we heat the flask, however, the dinitrogen tetroxide decomposes into nitrogen dioxide, creating more of the brown gas until equilibrium is reached for the higher temperature.
So they heated it up. When they heat it up, it's going to favor the endothermic direction, which is the reverse. So we add heat that's adding product, it's going to shift this left, making more NO2.
A solution of cobalt chloride is placed in hot water. It turns blue. It is then placed in ice water, and it turns pink. The process can be repeated.
So it's just, we got to figure out which one's the endothermic and which one's the exothermic. I don't have the reaction here. It's more of a Chem 1B Lewis acid-base reaction. This is Haber. Haber is very famous. This is one of these big reactions that have changed the world, kind of thing. And that is the reaction of nitrogen with hydrogen to form ammonia. Prior to this, farmers used to use things like manure and other things like dead crops to fertilize the soil. But this is the first synthesized fertilizer versus natural fertilizer that farmers use. And this increased the food production too, and actually benefited a lot of people in the world. Because I think food production became much more productive here. But this is a very hard reaction to accomplish. You know, it is very unfavorable. And so this guy is very famous, and this reaction is very famous as well. Here's the reaction here. They're creating liquid ammonia. If you cool down ammonia, it liquefies. You know, you cool it down to dry ice temperatures, it's a liquid. This is a clear colorless liquid. This reaction is going to be favored at high temperature or low temperature. This reaction is going to be favored at low temperature because it's exothermic. And so we want to remove the heat, which would shift this to the right. You know, if we remove product, the Le Chatelier's principle says the reaction is going to shift to compensate for it. And that's Le Chatelier's in temperature. This is exothermic too. So if we remove heat, that is cool it down, it favors the forward. If we add heat, it favors the reverse. This is exothermic also. This is endothermic. So if we add heat here, it favors the forward. This is another very famous reaction. So two very famous reactions on the same page. This reaction is the one I was talking about. And the Romans. Romans had lots of limestone, so they just heat it in their kilns to make calcium oxide, which is required for making cement, which is required for making concrete. And so this is a reaction in synthesizing Roman concrete. This reaction people don't want. This reaction, if you have a car, you have to bring the car to get smog checked, and you got to make sure the NO levels are not too high. That is, you know, nitrogen and oxygen can combust together. These are normally stable because this is air, but at very high temperatures, they can combust. This is an endothermic reaction. Very high temperatures and high pressures, they can combust to make NO, and the NO2 is, again, oxidized in air to form NO2, which is smog. Now, which side's favored? Which side's favored is often determined just experimentally, you know. And when we determine this experimentally, we get something called the equilibrium constant. The equilibrium constant is just a ratio. It's a ratio of the products over the reactants. And so this is the ratio. You know, each time they do this reaction, they'll start with different conditions. So they're doing different trials. So in experiment 1, they start off with 1 molar hydrogen and 1 molar iodine. And this is initial. And then they wait for the reaction to finish. Once the reaction is finished, they see they have a mixture. You know, not all the hydrogen reacted. They have 0.218, and that's not going to change because, you know, we reach this state of dynamic equilibrium. And the iodine's the same, and we formed HI. Now the ratios are correct. It's just the amounts. You know, normally when we're doing Chem 1A Chem 4 stoichiometry, we predict it's going to be complete reaction here, but it's not. It's not complete. We get a mixture of reactants and products at the end of the reaction. And that the mixture of reactants and products has a fixed ratio. This ratio is called the equilibrium constant ratio. And it's a ratio of the concentrations. And the concentrations are going to be raised to the coefficients. So HI is the product concentration squared because the coefficient is 2. And then we have H2 to the first and I2 to the first. So it's the products raised to their coefficients over the reacting concentrations raised to their coefficients. And that ratio turns out to be fixed. So no matter how we start this reaction, you know, we could start it with all product and half as much all product, or, you know, change the ratios. We always end up the same. And so we can use this ratio to predict where we're going to end up. No matter where we start, we have to end up satisfying this ratio. So this is called the equilibrium constant, K. And it's just the ratio of products over reactants. And so this is K, and it comes out to 51.5. And so we could use that ratio to make predictions and calculations here. Now, the bigger the ratio, the more product. The smaller the ratio, the more reactant. And so this is kind of a mix. You know, these numbers this K can be huge, or it can be extremely tiny. Well, this is neither huge nor extremely tiny. So we expect a mix of both reactant and product, and that's what's observed, a mix of both reactant and product by the end of the reaction here. Now that ratio is kind of funny because you look here, 0.532, 0.032, 0.936, you know, the ratio can be odd numbers depending on what you start with here. But when we calculate K, it's always the same number, 51.5, or it's supposed to be. Yeah, the same. This is reaching equilibrium, you know. This we saw in the vapor pressure thing earlier. So here, this is showing how to write the equilibrium constant. If I have a generic equation like this, then it's pretty straightforward. I don't think we have to break it down into so many steps like the book did here. But the K value for this, which we want to write here, the K value for this is going to be the concentration of C raised to the little c power, concentration of D raised to the little d power, divided by the concentration of A raised to the little a power, and the concentration of B raised to the little b power. And so this is going to be a constant. And so this allows us to predict, you know, no matter where we start off with here, we're going to end up here. And we can do calculations. This is Chem 1B style stoichiometry. You do a lot of these kind of calculations in Chem 1B. And so this is the equation that they get. And so we can do different equilibrium type constant expressions here. Oops. Now, when we have a liquid in there and solids, we don't include those here. It's only aqueous and gases we're going to include in a K with the concentration. So here, the hydrogen's a gas, the oxygen's a gas, but H2O is a liquid. The reason why those don't appear is because the concentration doesn't change. You know, if you have pure water, let's say you have a glass of pure water and you drank half of it. So you have a half a glass of pure water. The question is it half the concentration? No, it's still the same concentration. It's still pure water. And so it's still 100% water, even if there's only one drop left there, you know. And so concentration of pure liquids doesn't change. So we could, you know, we could lose half the water that was there originally, but its concentration doesn't change. And the same thing goes for solids. Solids are not going to be in the ratio here. And so the product is just solid. So instead we'll call it 1. And then that's what we do for liquids too. Liquids and solids get 1. So cobalt 2 chloride is going to be 1. And but water's a gas. Gases and aqueous will appear here. So this will be H2O to the 6th power. Now the significance of the value of K, you know, the K, the bigger the K, the more the products are favored. Wow, look at the K value on this is 10 to the 33. So it means it's all product, very little reactant here. And so this is a very favorable reaction. Hydrogen gas and chlorine gas. Very favorable reaction. And so it could be huge like this, or it could be extremely small, you know, extremely small. And so if an equilibrium constant is very large, greater than 100, the forward reaction is favored. If the constant is very small, less than 0.01, then the reverse reaction is favored. If it's between this, neither large, or very small, then we have all species. All species are present at equilibrium. And so greater than 100, it's mostly product, less than 1/100th, mostly reactant, and in between there, it's everything's present. So this is mostly product, 10 to the 9th. Forward reaction is favored. It's about 300, and so all species, but a little bit of more product. And so all species. Now, let me just, we aren't going to do a calculation, equilibrium calculation. This is optional. But this is how you would do the stoichiometry in these, because, you know, the target is the ratio at the end. And so if we have some kind of calculation and we want to try to find out, you know, where it ends up, then we do, let me show you type of calculation. This is figuring out what K is. You know, there are different ways we can figure out K. See. Okay. Here, like this.
The flask contains water. Nitrogen monoxide gas is bubbled into the bottom of the flask. As the bubbles break the surface, they form a brown gas. After a while, the NO gas forces the brown gas out of the flask. Air is injected into the top of the flask, and the gas turns brown again.
So if we want to figure out the stoichiometry of that, we have to do this type of equilibrium stoichiometry. And equilibrium stoichiometry, let me just briefly give you, this is not going to be, although maybe not going to be on the test, but we set up a table like this. This table is called the ICE table. ICE. And so I stands for initial, C stands for change, and E stands for equilibrium. And then we fill out this table. And so at the end here, at the equilibrium, this is where we're going to end up. So what's the ratio of product to reactant at the end? Well, we know what the ratio is if we have K K will tell us the final ratio. But what those numbers are going to be are going to depend on what our initials here are and what our change is, you know. And so we use an ICE table like this to figure out reactions. Okay, again, this is optional here. So let me see if they have one of these filled out. Here's an ICE table. Okay, well, let's take a look at the homework problems here. So reversible reaction, equilibrium, forward rate, brief description of relationships. So let's just read it. A reversible reaction reaches equilibrium if the forward reaction rate is equal to the reverse reaction rate. Collision theory of chemical reactions, energy reaction progress graph. I call this reaction progress, yeah, graph, I guess. Transition state, activation energy. Collision theory, yeah, molecules or particles got to collide, energy and, you know, orientation. Transition states is a temporary thing where the bonds are breaking, and it's a transitory state. So that's the state at the very top of the activation energy. Activation energy is the amount of energy required to make the transition state. And the transition state is what you need to get, you know, that's a state where the bonds are breaking, the bonds are forming. That's what we need to get the product. Temperature, catalyst, concentration, reaction rate. So these are just little definitions. Le Chatelet's principle, temperature, gas, volume, concentration. Let's read these. You have the anchors of these. Equilibrium constant. We have different types of equilibrium constants. We have KW, which is for water. We have K, which is just in generic. We have KP. We have KC. KP stands for gases, pressure. KC stands for concentration. We have KSP. KSP is solubility product, which is for salts, insoluble salts. We have Ka. Ka is for acids, acid and water. So we have different kinds of Ks. Oh, that was not actually the questions. These are the questions. What does it mean when an equilibrium is described as dynamic? Compare an equilibrium that is dynamic with one that is static. Okay. A dynamic equilibrium, there's no change at the macroscopic level, but at the particular level, there's continuous change. In the static equilibrium, nothing's changing. Undissolved table salt is in contact with a saturated salt solution. An open beaker, which system, if either, can reach equilibrium? Explain your answer. They're both at equilibrium. A garden in a park has a fountain which discharges water into a pond. The pond overflows into the stream that cascades to the bottom of a small pool. The water is then pumped up into the fountain. Is this system a dynamic equilibrium? Yeah, this would be a dynamic equilibrium because the water is flowing down and then they're pumping water back up. So water is going both ways. And the level of the pool to both the top and the bottom shouldn't change. Okay, well, I guess they're saying it's not, this is not an equilibrium because energy must be supplied to keep it in operation. Also, the water is circulating, not moving reversibly. Okay. Well, energy is involved in all chemical reactions. But I see what they're saying. They're having reversible, but you know, the reversible reaction does not necessarily have the same mechanism. So this is too simplistic of an answer, I think. An equilibrium. So in that case, this would not be equilibrium here, you know. I know this is not equilibrium because the water is just going to flow downhill here, but if you're pumping water back up, then It's dynamic in the sense that water is moving down and up, and it's at equilibrium because the water levels aren't changing. Because if the amount of water going down is the same as the amount of water being pumped up, then there's no change macroscopically. Yeah. Explain why a molecular collision can be sufficiently energetic to cause a reaction, yet no reaction can occur as a result. It's because orientation, right? Orientation. Sketch an energy versus reaction progress graph for an endothermic reaction. Include A, B, and C points on the vertical axis and use them for the algebraic expressions of delta E on the graph. So with the reaction progress diagram, what we do here is this. This is just the progress on the y-axis. This is progress. And so over here, we start off at reactants. And then there's going to be a hill, you know, the activation barrier, which we call E sub A. Now, if it's endothermic, then the products are higher in energy. And so it's an uphill climb. This is our delta E. Our delta E is just the energy difference between the reactant and the product. But we also have this hill to climb here. This is E sub A, the activation energy. And so it's got to get up this hill and then drop down here. But overall, it's endothermic. Overall, we need to go up in energy in this particular example. A, B, C. So this would be A, and then B here, let's say, and then C here. We can make equations using A, B, and C. And so activation energy is this big one here. Assuming the reaction described in figure 18.3 to be reversible, compare the signs of activation energies, which is positive, which is negative, or if they're the same. Oops. Here, this is activation energy in the forward direction. Can I scroll? Both are positive. And so you got a hill, this hill to climb, or if you're going backwards, you got this hill to climb. So both are positive. One's just bigger than the other. Both the activation energies are positive. One's bigger. Well, what is the transition state? Why is it that we cannot list the physical properties? The transition state is, it's only a transitory state. It's not something you can capture and study. You know, it's a state where the bonds are breaking and the bonds are forming. And so it's the middle of transitioning from the reactants to the products. So, Spartan does transition states, so you can make them and then study them that way, but you can't capture them to study them, you know, in an isolated way. Here. So here's this transitory state where the bonds are forming here and bonds are breaking. Actually, in this case, these aren't. And so this NU-C bond is forming. NU is called a nucleophile, and the CBr bond is breaking. So in this transitory state where this bond is starting to form and this bond is starting to break, you can't isolate it because there's no bonds there. It's just starting to form and starting to break. Note, the transition state structure has partial bonds, can't be isolated here. It's right at the top, at the peak here. We can isolate the reactants, of course. We can isolate the products, but we aren't going to be able to isolate this transition state. We can use Spartan to make this transition state and then study, you know, what we expect its properties to be. but it's unstable. It's either going to fall backwards to this or it's going to fall forward to this, to the product here. It's a transitions. Transition state occurs right at the peak of the hump. Another transition state. So we could use Spartan to make these things to see what it might look like. Here, there could be multiple humps here. There's another transition state here. Some more transition states. This is 2 humps here. One activation area here. So this is 2 steps. We can isolate something called an intermediate. And intermediate is here. It occurs in this well. This is TS1, is transition state 1. This is TS2, transition state 2. Those aren't isolated. Here's another transition state here, this triangular type deal here. Here's somebody sketching out the transition states, you know, what's happening. This is a mechanism here showing how the electrons are rearranged. So this is the Lewis base here attacking that's Lewis acid. Too many bonds, so gotta make it. So this is some kind of transition state here, and that's the product. So this would be at the top of the hump. You can figure out how high this is by comparing the energy of this versus the energy of this in Spartan. That's going to be the hill you have to climb in order to get over to the product. So do that. Some more transitory states here. Here's a couple of transition states here too. Transition state 1. This intermediate can be isolated here. This can't. This has actual bonds. Isolated means you can measure properties. Sometimes people try to probe it, you know. These reactions happen very fast. And so you need a very fast laser to probe this. And so people are looking at like, what did I see? Very fast laser. And so either like very, very high frequency, like I saw a building. I was at UCSB the other day. I saw a building called terahertz. Oops. It's UCSB is a terahertz facility. Terahertz is extremely fast. Here.
Professor?
Yeah.
It's break time.
Okay, we'll stop now for a break. Okay, let's take a break. We'll start again in 15 or so. Okay, what we're going to do for the last part, let's see. I'm going to open up some breakout rooms, and then what you guys can do is that you guys can work on the labs that we have. And so let me go ahead and open the rooms. Here. And you can work on the labs, and if you have some questions, go ahead and post your questions. I'm going to end lecture for today, so we'll finish up 18 and 19 probably tomorrow. So.